The 113th element NIHONIUM was found in Japan. This new element was discovered by a Japanese research team based at RIKEN, the Institute of Physical and Chemical Research. However, theoretical research on nuclides led by principal researcher Koura of JAEA has also contributed to this discovery. Here, Dr. Koura will talk about the world of super-heavy elements, including NIHONIUM. Let's take a look at the periodic table of elements. This is a table until October 2016. Elements are arranged in the periodic table in the order of their atomic number, from hydrogen, then helium, and so on. But there are still some areas of nuclides with large atomic numbers, of which not much is known. Here, elements with atomic numbers of 89 and above are called actinides, and those with atomic numbers of 104 and above are called transactinides, or super-heavy elements. In this periodic table, you can see names are not given for the 113th, 115th, 117th, and the 118th elements. However, the symbols and names for these elements were officially determined last year. As a result, on November 30th, 2016, names were determined for all elements in period 7. An atom consists of electrons and a nucleus consists of protons and neutrons. The number of protons and neutrons determines the property of the nucleus. Keeping that in mind, let's journey through the world of nuclei. How many nuclides are there in our world, do you think? This is a chart showing nuclides which are around us. From this chart, we can see that nuclides exist in the shape of a narrow bow. These are the 280 and more nuclides that exist stably in the natural world. In our research on nuclides, we create new nuclides by combining these nuclides. This figure shows nuclides which were created by such a method and identified experimentally. In this figure, discovered nuclides are listed by age. More than 3,100 nuclides have been experimentally identified as of 2014. Looking at this area of particularly heavy elements, it is apparent that there is an area which has expanded rapidly in the last 20 years. This is the area of elements called super-heavy elements or super-heavy nuclei. As many as 3,150 nuclides have been experimentally identified to date. However, the research team led by principal researcher Koura predicts that far more nuclides exist in our world. What's needed to predict nuclides is a theoretical calculation of them. At JAEA, we conduct systematic theoretical calculation for nuclides, including unknown nuclei areas like super-heavy nuclei. This is a model we use called KTUY mass model, named after the researchers involved. Using this model, we comprehensively calculate and predict the nuclear structure, decay modes, half-lives, and so on for various nuclei. And so, nuclides are synthesized artificially. But when you look at such an expansion in the number of nuclides, you may wonder how many nuclides can exist in our world. Some theoretical predictions indicate nuclides exist in a far broader range than which is shown in this chart. This is an example of theoretical calculation. Experimentally identified nuclides are shown. However, it is theoretically predicted that nuclides exist in a broader range like this. You may notice here in this figure that existence is predicted for this roundish area in particular. This is an area of super-heavy nuclei. This is called the island of stability of super-heavy nuclei. While one of the main aims of research on super heavy nuclei is to explore how many nuclides can exist in this world. Another is to identify this island of stability of super heavy nuclei. Interestingly, some say nuclides with long half-lives may exist in this island. The 113th element has a half-life of milliseconds, but some predictions state that there would be nuclides with half-lives of hundreds of years or tens of thousands of years at the center of this island. The search for such nuclides has been ongoing since the 1960s for the possibility of using them as materials. Thus, theoretical calculations are conducted for an extremely wide range of nuclides. JAEA has been collecting data on the decay of atomic nuclei from around the world and making these data available to the public. JAEA publishes the data in the JAEA Chart of the Nuclides. This is a project to compile all the nuclear decay experimental data in the world. The chart has been published since 1977 and is updated every 4 years or so. The most recent version is a Chart of the Nuclides 2014. This is a Chart of the Nuclides 2014. It includes experimental nuclear decay data and includes theoretical decay data for unknown nuclides calculated by the KTUY mass model. In this way, our KTUY mass model is utilized for compiling nuclear data. As an example of that, I would like to talk about the story behind the discovery of NIHONIUM. This is a JAEA Chart of the Nuclides 2000. At this time, NIHONIUM had not been discovered by RIKEN yet. However, in this chart, we had already given a theoretical prediction of NIHONIUM-278, which was later synthesized by RIKEN. Here, it reads alpha 221 microseconds. This is a theoretical prediction of a nucleus with alpha decay dominant decay and a half-life of 0.2 milliseconds. This was predicted in 2000. When RIKEN actually synthesized this nucleus, they experimentally obtained a half-life of about 1.4 milliseconds. The accuracy of a theoretical prediction on half-life is about 1 order of magnitude, and we successfully predicted the actual value within this 1 order of magnitude error range. Now, I'd like to talk about what the future prospect of super heavy elements is like, theoretically speaking. We usually don't have to think about the lifetime of elements existing around us. They have near-infinite lifetimes. However, NIHONIUM is not practical to our lives, although it is significant academically. NIHONIUM decays quickly. Almost all super heavy nuclides have short half-lives. But if the half-life is long, in the order of years, hundreds of years, or tens of thousands of years, then such nuclides can be used as materials. We will then be able to use them in our lives. The search for such usable materials is one of the aims of research on super heavy elements. This element, darmstadtium, is located here in the periodic table, right beneath the platinum group. Therefore, when we gather darmstadtium into lumps, they may show metallic luster just like platinum does. Some theoretical predictions indicate distribution of nuclides even for an area with neutron-rich heavy nuclei. I believe that, in the future, research should focus on experiments on super heavy nuclei in this area.